Okay, so I hope you can see my screen.
Yeah, it's okay. Yeah, it's fine. Yeah, perfect.
So in the last few lectures, uh, what we have seen is a basic overview of the theory of mapping class groups and how this mapping class group acts on the Teichmuller space, right? So today we'll be discussing a classification theorem. Okay, the plan of the talk is to basically state the theorem to understand what exactly is going on. Okay, so let me start. So we'll start with the mapping class group of the torus. I hope you remember the definition of the mapping class group. What you do, you consider the set of all orientation preserving homeomorphisms from the torus to torus, and then you quotient by the identity component. So basically you see the homeomorphisms up to isotopy, right? That forms a group and that is called the mapping class group. Now, so given a homeomorphism G, right? From so S1 here is a torus, right? It's a genus 1 surface. So we are denoting it as S suffix 1. So given a homeomorphism G from S1 to S1, uh, what it does is it induces a map at the level of the fundamental group. In this case, as you know, that the fundamental group of the torus is Z cross Z, Z2, right? So this will induce an automorphism as it's a homeomorphism. It will induce an automorphism G star of pi1 S1, that is Z2. Okay, and the set of all automorphisms of Z cross Z is nothing but GL2Z. Okay, the matrix 2 cross 2 matrices, invertible matrices with entries in the integers Z. So our G star belongs here, GL2Z. Okay. Now, if you consider two such homeomorphisms from S1 to S1, say F and G, which are isotopic, this means they belong in the same mapping class, right? You can see that F star and G star will be conjugates. Okay, inside your GL2Z, these will lie in the same conjugacy class. So this gives a definition of a map from the extended mapping class group. Okay, I'll define what is this, to GL2Z. What is this extended mapping class group? This is basically you are not restricting to only the orientation preserving homeomorphisms. So you are also allowing the orientation reversing homeomorphisms. So it's basically the mapping class group is an index 2 subgroup of this extended mapping class group. Okay, we are denoting this as mod plus minus of S1. Okay, so given any element G, or say class of G, it's a mapping class, we are getting a conjugacy class of G star. And now if you restrict this phi into this index to subgroup, namely our mapping class group, what you can see that the restriction is actually an isomorphism between mod S1 and SL2Z. Okay, so it's very, the mapping class group is a very, yeah, Neeraj.
Sorry to interrupt. I am not getting this map. Maybe I am missing something. Sorry for that. But this map is from mapping class group to GL2Z. So,
Right.
so if you take the two isotopic classes, they will go to conjugate elements. So
Right.
is it not is how is well defined, map? Because you have to pick a conjugate.
Right.
I think the mistake in the fact that in my understanding is if they are isomorphic, if they are two map isotopic, then they will induce a same map on the fundamental group. Actually, on the fundamental group, they will be equal.
So you are saying G star and F star is equal?
Then only this map makes sense.
I think the class and a class of G and F are equal. G star and F star equal.
Sorry,
I think yeah, you are right because the class of F star and the class of G star should be equal.
there is no class. Like F star is a one homo automorphism of the fundamental group. There is no class in that.
Let me check once.
So two maps are the homotopic. Then they will induce the same isomorphism on the fundamental group. That I think is true. I'm not sure. Please correct me if I'm wrong. So otherwise, this map is I'm not getting why this is well defined. Because you can choose a two representative, they will go to some different elements. Even that elements are the conjugate, so you will go up to conjugacy, and then you will not lie in the GL2Z, but in the quotient of that. So yeah, please, yeah.
Right. Uh,
I mean, if they are isotopic, then the induced map will be equal. That is true.
Thanks, Praveen.
okay. Right. So this the source I am looking at currently. This says that yeah. So homotopic homeomorphisms induce conjugate automorphisms. Isn't it true?
So in which sense you are looking this? Like I'm not still I'm not like I'm not convinced, because as Praveen is pointing, I think it's
Okay. So you're
homotopic
saying
homeomorphism.
it should be equal, right? Yeah. I
Yes,
also
yes.
doubt. Yeah. Hmm.
If it is not equal on the on the fundamental group, you go to homology. Wherever it's equal, then only it makes sense.
Okay. So let us stick to equality here. So if this is true, okay. So this is just G star, right? Okay. Okay. So the class of G goes to G star, and then it's an well defined map. Okay. So this map is well defined now. Now, yeah. So to restrict this map on the index to subgroup, namely our mapping class group, uh, this can be shown to be isomorphic to the subgroup SL2Z. Okay. So you need to see that this map is surjective as well as injective. Okay. So this can be checked. Now, the same construction can be generalized in case of surfaces which are of genus greater than equal to 1 also. So strictly greater than 1. So we have this theorem, Den-Nielsen-Baer theorem, which states that for any surface S, which is closed surface of genus G greater than or equal to 1, the extended mapping class group is isomorphic to out of the fundamental group. So out means the outer automorphisms. Okay, so you quotient your automorphism group by the inner automorphism group. Okay, so you can see a proof of this in the Farb-Margolid book in theorem 8.1. All right. So our aim is to see this this mapping class group of the torus, which is we have seen as SL2Z, the matrix group. Now we'll see some specific example of elements here. Okay, namely, you consider the matrix A, which is 2 1 1 1. Okay, now it has trace of this matrix. If you calculate, it's 3, right? So you could have considered any matrix which has mod of trace of A is greater than 2. Okay, so in particular 2 1 1 1, if you choose and you calculate the characteristic polynomial, which is x square minus 3x plus 1, you calculate the eigenvalues. Okay, let's call them lambda and 1 by lambda. So it's coming out to be 3 plus root 5 by 2 and 3 minus root 5 by 2. Now you look at the eigenspaces of this matrix. Okay, if you calculate, you will find this. So the one of the eigenspace will give you this multiples of this this vector 1 plus root 5 by 2 1, and the other one which we are calling E of 1 by lambda, this will give you all real multiples of this vector 1 minus root 5 by 2 1. Now let us draw these eigenspaces in our Euclidean plane. So at first we draw these vectors, these vectors 1 plus root 5 by 2 and 1. So this is basically this matrix, this vector. Okay, this one is our 1 minus root 5 by 2 comma 1. I guess no, this is 1 plus, and this one is 1 minus root 5 by 2 comma 1. Okay, now if you calculate some of the distances here, you can see that the image. Okay, so I have drawn these parallel lines. So we have two vectors here. Okay, these green vectors, and say you take this vector 1 plus root 5 by 2 comma 1, right, and you consider all parallel lines in R2 of this vector. So yeah, so this will give you a foliation of your plane. Okay, such a construction, such a family of disjoint curves which fill your whole surface is called a foliation. Okay, and similarly for the other vector, the other vector is 1 minus root 5 by 2 comma 1. If you consider all parallel lines, okay, to this vector, this will also fill your whole plane, and this is another foliation of R2, right? Now if you apply this matrix A on R2 now, and you see where these foliation leaves are going, you can see that the images are somewhat like this. So okay, and the other foliation will be something like this. So what is exactly happening? In one direction, the foliations are getting stretched. The leaves of the foliation are getting stretched, okay, namely in this direction, right? In this direction, they're getting far apart, and in this direction, they're getting contracted, right? So such a dynamics is going on here, and so we are noting here that if we call these foliations as f1 tilde and the other one is f2 tilde, so f1 tilde is getting stretched and f2 tilde is getting contracted. And if you see the actually calculate uh, the the amount of stretching here, you will find that the stretching is by a factor of lambda, and the contraction is by an factor 1 by lambda, which is our uh, this eigenvalue, these two eigenvalues. Okay, so so it's in this example we're seeing that such a matrix or such a map on our uh, R2 will give us two such transverse foliations, right? See, these two foliations are like at a right angle, right? All these, if you consider any leaf of the first foliation, it is a 90-degree angle with the other any other leaf from the second foliation, right? So they are called transverse foliations here, and the foliation which is getting stretched, let us call them unstable foliation, and the other one which is getting contracted, let us call that foliation as stable foliation. And this particular constant lambda, okay, we are calling it a stretch factor for this map. Okay, these are just terms. Now you notice that we have the standard covering map from R2 to the torus, right? From R2 you can go to the torus by the standard covering map. Let us call that P. Now it can be checked that uh, if you look at the foliations above in R2 and you project them to the torus, it will give a foliation on your torus also. Okay. So this f1 tilde will induce a foliation f1 on your torus, and f2 tilde will give a foliation, let's say f2 on your torus, and they will also give a transverse foliation. So this transversality will be preserved there also, and locally these uh, this dynamics it will be preserved. So in there will be two directions, right? At every point there will be two directions, and in one direction the leaves will get stretched, and the in other direction the leaves will get contracted. Okay. So such a homeomorphism A is called an Anosov map on our torus. Okay. So yeah. So we'll try to generalize this notion of an Anosov map of the torus on any higher genus surfaces. Okay. So let us define what is called a pseudo-Anosov element of the mapping class group. Let S be any surface. Okay. An element, for the time being, you can consider, say, S is a closed surface. Okay. In fact, these can be defined for punctured surfaces as well. For the time being, let us fix this as a closed surface of genus G. An element F in our mapping class group mod S is called pseudo-Anosov if there is a pair of transverse measured foliations, F unstable and mu unstable, and F stable, comma mu stable on S. So I'll not be defining what are these terms, but we have seen what is a foliation on R2 and the torus, right? In case of a general or higher genus surface, also there is something called singular foliations. Okay, so I'll not be defining what are they, but by singular I mean so you can find uh, a collection of curves on your surface, okay, which are disjoint, and they fill your surface apart from some singularities. Okay, so by a singularity I mean it's a one-dimensional submanifold, okay, sitting inside your surface. If you remove that submanifold from from your, it's not a submanifold in fact, okay, so it's a one-dimensional subspace rather, uh, if you can define what is the dimension there. So okay, so if you remove such a singularity, then the rest of the surface you can fill using these disjoint lines or curves that you have seen just in R2. In R2 there is no singularity here, okay, but in case of higher genus surfaces there will be some singularities, and such a foliation is called a singular foliation. And what is called measured, so you can define a transverse measure on your foliations just to make sense of this stretching. See here we are stretching these foliations, right? Just to calculate these how much they are getting stretched, we need this some kind of a measure which is called a transverse measure. Okay, so these mu's are basically those transverse measures. All right, so let me again repeat. You have a surface, for example, let it be SG. An element F from your mapping class group is called a pseudo-Anosov element if there is a pair of transverse measured foliations. One is FU with mu U, and the other one is FS, okay, mu S. Here U is telling us the unstable foliation, and S is basically the stable foliation. And also you have a real number lambda which is greater than 1, and a homeomorphism which is basically representing our mapping class. So from our mapping class F there is a phi which is a homeomorphism such that if you apply your phi on the first unstable foliation, you see the measure is getting multiplied by lambda, okay, and in the other foliation Fs, if you act your phi on the other foliation Fs, then the measure here is getting multiplied by a factor of 1 by lambda. So here also there is a stretching and contraction going on. Okay, so locally the same behavior that we have seen above, this behavior, okay, this is locally is there in your surface, okay, by this particular phi. Okay, such a map F or mapping class F is called a pseudo-Anosov. And as I said earlier, the first foliation which is getting stretched is called the unstable foliation, and the foliation which is getting contracted is called the stable foliation. And as usual, the lambda, the constant that is getting multiplied is called the stretch factor of the mapping class. Any questions? Okay, so now let me define or state. We are now ready to state the theorem, which is the Nielsen-Thurston classification theorem. Okay, so you start with any surface. So that surface can have punctures also, as I mentioned earlier. So genus G with n punctures, where G and n are greater or equal to 0. You consider such a surface S, and given any mapping class of mod S, okay, in mod S, there can be three possibilities. Either there is some homeomorphism inside that mapping class F, say phi, such that phi is periodic. By periodic, I mean it is of finite order, right? Or there could be a phi inside your mapping class such that phi is reducible. Reducible means there is a multi-curve sitting on your surface which is preserved by this phi. And the third possibility is if none of the above is true, okay, then there exists some phi in your mapping class F such that phi is pseudo-anosov. Okay, so there are three possibilities. One is periodic, the other one is reducible, and the third one is pseudo-anosov. Now, as I pointed out in the last talk, that there could be a mapping class which is both periodic and reducible, right? We gave some example. But a pseudo-anosov is never periodic or never reducible. So this theorem is telling us that a mapping class which is not reducible, not periodic, it should be pseudo-anosov. Okay, is it clear, the statement of the theorem? Now let me give a way of uh, constructing some examples of pseudo-anosovs. So Robert Penner in 1988, he wrote a paper where he described a construction, a method to come up with some examples of pseudo-anosov elements of some mapping class group. And he conjectured that any pseudo-anosov element can be constructed by this method, okay, which later was proved wrong. So this method will not give you all possible pseudo-anosovs, okay, but they are a very good family of pseudo-anosovs. Let me tell you about it. So for that we need one definition. I have already mentioned this notion of filling curves. Let me again repeat. So you have a surface S, a collection of simple closed curves on your surface S, say gamma 1, gamma 2, up to gamma n, some finitely many uh, collection of curves. They are said to fill S. Okay. If what happens, if you remove these curves from your surface, whatever is left out, these are basically some disjoint union of disks. Okay. So if such a thing is happening, then you say that this collection of curves will fill your surface S. Okay, the definition is clear, right? All right. Now, let us move to the construction here. You start with some A and B. Okay. Let A is a collection of disjoint curves, say alpha 1 up to alpha n. Okay, these are disjoint. And B is also another collection of disjoint curves, beta 1 to beta m. Okay, such that A union B fills S. So this means you consider the union of these two collections. Okay, see, the first collection are like alpha 1 to alpha n. They are disjoint, this is given. And also all the beta i's, they are disjoint among them. But when you combine them, they may not be disjoint. Okay, some alpha I may intersect some beta j. That is allowed. Okay, so the assumption is A union B fills your surface S. Then any product of positive powers of dentwists T alpha I, okay, you know what is a dentwist, right? We have defined what is a dentwist along a curve. So you consider these alpha i's, and for each of these alpha i's, you have a dentwist, which is T alpha I, right? Okay, so you have n many dentwists T alpha I, and you take their positive powers. So you can take T alpha I or T alpha I square or cube, something. And some negative powers of dentwists T beta j. So you do what? You do the same thing corresponding to each beta I or beta j. You consider the dentwist along them, T beta 1, T beta 2, T beta m. So you have m many dentwists. And you consider negative powers of these. By negative power, I mean T beta 1 inverse or T beta 1 to the minus 2, T beta 1 to the minus 3, something like that. Okay, so you have two sets of powers of dentwists. One is positive powers of T alpha I, the other one is negative powers of T beta j, and you have a product of all of these. Okay, such that only one condition is there, that from for each of these alpha i's and beta j's, okay, at least one candidate should be there. So say T alpha 1 should appear at least once in that product. Same for others. So T beta 1 to the minus 1 or minus 2, something. That should be there at least once. It may have repetitions. Two times they can come in different places in the product. But at least once they have to come. Okay. Then the theorem is saying that any such product, okay, this will be my mapping class, right? That is a pseudo-NS of element. Okay, this is actually a great theorem, right? So let me give one example. So we have genus 2 surface here. Okay, and I have drawn two family of curves, right? We can name them. Say this is our alpha 1, this is our alpha 2, alpha 3, and say this is our beta 1, this is our beta 2. So what is our A? Sorry. What is the collection of A here? It has three curves, right? Namely alpha 1, alpha 2, alpha 3. You see, these are mutually disjoint, right? They do not intersect with each other. What is B? It has two curves, beta 1, beta 2. Same here, beta 1 and beta 2, they do not intersect. So our first condition that they should be multi-curves, This is satisfied. Now, you need to see here that A union B, if you consider all of them together, this will fill your surface. This means if you remove these curves, okay, from your surface, all of them, then you will land up with a disjoint union of some disks. Okay, so you can check. You can actually check this. Uh, can you guess how many disks will be there? Yes. Can you help me with this? I have not thought about this, so let me do it in front of you. So if you remove this alpha 1, what you will get is something like this. So you have, right? And also suppose you remove alpha 3 here. So okay. Now this beta 1 is still there. Suppose this arc will be there as beta 1, and this will be our beta 2, right? Please correct me if I'm wrong. This is our beta 2, this is our beta 1, right? And alpha 2 is still there. What is alpha 2? Alpha 2 will be this. Now we want to cut these also. Okay, so suppose yeah, let's cut along this alpha 2. So we have two disjoint components, right? If we cut along this alpha 2, we will have two pair of pants. It will be something like this. So you have this here, this here, this here, something like this, right? And also below you have right, but still you have these parts of your beta eyes. Where are they? They are here, right? And you also cut them. So what you get, you will not get disk, right? No, you will get.
Actually,
You will get.
you will get a disk. It's a 8 gone.
You,
Two
exactly.
discs.
Two disks you will be there. Exactly. Thanks. So if you cut here, all the boundary components will be now one connected boundary component. So you will get something like this. Yeah. Perfect. So we have proved that this collection, okay, this A and B, they together fill our surface S2. Yeah, we are convinced now. So now this theorem is telling us that if you consider any product of dentist, so let me write down the dentist here. We have T alpha 1, T alpha 2, T alpha 3, T beta 1, T beta 2. Now you need positive powers of these and negative powers of these. Okay, and each of them should appear in the product at least once. Okay, so this is the rule. So let me start. One such example would be this, say beta 1 inverse, right? So if this is our some mapping class, which is a product of these den twists, this is a pseudonymous of element by the above theorem. Okay, so just to understand that most of you have understood, can someone else tell me some F2, another product? Yes. Come on. Any other example? There are a lot of them, right? Devottam, you want to volunteer?
Yeah, you can choose T
Yeah.
alpha 1 and T alpha 2 inverse. Right.
No. T alpha 2 inverse is not allowed. You see, we
Okay.
need positive powers of T alpha 2.
Okay. So I just can take another representation of this.
Tell me.
Uh, just change the position that T.
Sorry.
Hello.
Yeah.
Yeah, just change the position that T T beta 1 to T beta 2, and
I don't understand. Can you just tell me one example?
yeah, and one should appear and one must appear, right?
Every one of them should appear
Yeah,
anywhere. The ordering is up to you,
yeah.
but at
Just
least one.
okay.
Ah,
I'm just saying the change the order actually. Take T alpha 1 and T beta 1 inverse T alpha 3 and T alpha 2.
okay. Let me write one. So T beta 1 minus cube, T beta 2
Yeah,
minus 5, yes, T alpha 2 and T alpha 3 to the 100.
yeah,
Okay. So any such product will give you a pseudo sub element. Great. So it seems whatever I plan to say is finished. The content is finished. So if there is any question, I'll try to answer them. Some doubt or
Okay, so if there is no any question, we can discuss about the confusion we had on the page one.
acha. You mean the
That
map?
the conjugacy problem. Yep, yep, yep. Actually, what you have written is actually correct. These two maps are not equal. They will conjugate.
Why is it?
So technically, uh, when when I was saying this, my understanding was to isotopy also. What the isotopy we choose whenever we say on the two homomorphism on the maps are the isotopic, we think they preserve the base point, and if they preserve the base point, they will go on the same mapping fundamental group and so on things. But here, I think you are choosing a base point free fundamental group, so something I there. So it will be go to conjugacies.
But
Uh,
then but then how
yeah,
this?
as a start.
This GL2Z,
This
if you consider all the conjugacy classes, what will be
that's
there?
the same. That will be same because inner automorphism for the jet power 2 is actually trivial. So that's your Nielsen-Bayer theorem says. It goes to outer automorphism. But for the Z square, outer automorphism is same as automorphism. So it's complete GL2Z2. GL2Z.
So you're saying both the definition are giving us same, right? So
No, no,
if,
no, no. On the case of torus, yes. Because on the
huh,
case of torus, the fundamental group is actually abelian. So, so even they are conjugate, they are in this something inner automorphism is not. There is no any inner automorphism. So inner automorphism is not anything there. I think, and equality is because in the torus, this is a, I think this homology is the same thing. So on the homology, they will become a, they becomes a equal. So if you're looking the action on the homology, then they will
hmm.
equal. But on the fundamental group, they'll conjugate. I think you was correct, but still, I need little bit time to check it out. But I think you are correct. So I was just want to clear out
Oh,
this that my thinking was wrong. So
yeah,
please,
thank you. So let me
yeah.
let me make it a question mark so that we can think about it.
Yeah, so this is actually because on the torus fundamental group homology free homotopy is actually everything is Z square because it's a abelian group. So there is no problem you can say is equal because on the homology they are equal, but in the other cases it's not. So they will go in the conjugacy classes because of changing the base point will change the group structure a lot. So that's I think the base point problem is there. I'm not very sure about this. Again, I'm saying maybe, but equality will not be. This will be conjugate. I think yeah, whichever notes you were
Achha,
reading there.
so
The
what are the conjugacy classes in GL2Z? Do you know?
GL2Z I don't know the conjugacy classes. So the notes you were looking for that maybe have something about
No,
this.
that doesn't have the proof. Yeah.
They what they were saying is going to be the something like in mapping class group to auto. Yeah, so it says that surface is this. Whenever surface is negative curvature, the universal cover is contractible. So this is a kg on spaces. Thus, free homotopy classes of unbased map will correspond to conjugacy classes of homeomorphism of the fundamental group. This is something saying
Conjugacy class of automorphism.
Margaret
Hmm.
of homomorphisms of pi 1 to pi 1.
Aha. As it is a
This
homeomorphism,
is a
right? It
yeah,
would be
it's
automorphism.
auto
Yeah.
yeah, it's automorph. So yeah, you are correct. I think they need a negative curvature for conjugacy to be conjugacy class, and for torus they might be equal because the homology and the fundamental group is same. On the homology they are equal. That is again I think true. And that's why torus case is special. This is also if I check it in the market, then maybe something. So yeah, you put a question mark here, so that will be better. So it's need to check a little bit. One very careful about this. Yeah. So yeah, for that you need a negative curvature at least where I am reading. So
Hmm.
in the torus, this is conjugate or equal. That's we need to check because in the torus is not a negative curvature.
But finally, you will end up in SL2Z, right? For mapping class,
Yeah,
right?
yeah, yeah, that is true. Mapping class group of torus is SL2Z because like when I read it, it's like I'm going to homology, but on the fundamental group I am confused. On the homology, the maps are equal, but in the fundamental group I'm not sure. So sorry for that. Yeah, I will check it out, and maybe
Yeah. Okay. Thank you.
maybe someone else knows, then they can correct.
Any other questions like related to the this example? Is it clear? Like you have some questions? Because this is, if you understand this, it will be easier for you to appreciate what is the definition of pseudo-solve. Okay. Yeah, I think there is no question.
So if there is no any other question, let me again comment one more thing. You gave the example of the finite order map, which is reducible to.
Yes.
So natural question is every finite order is reducible? So what is your comment on that? Like, no, what?
I don't know. Maybe you can comment.
No,
I hope
I'm not sure. I'm
if
not sure that.
every finite order is reducible, then the theorem would be either it is reducible or pseudo-solve, right? But they're saying
That's
it's fine.
that's obviously true. So it's either reducible or. So
But
no,
I think
I'm not sure. What is the reducible definition of the reducible? Can you recall?
it says that this preserves some multi-curve. Multi-curve is a disjoint union of curves, simple closed curves.
Okay.
So preserving means you are allowing them to permute,
Mm-hmm.
right?
So no, answer is no, I think.
Of
Yeah.
course, the answer is
Again,
no.
yeah, answer is
Yeah.
no. And the example is you just take the any polygon and one click rotation. That will be the case.
Yeah. Thank you.
Yeah, that will be multi curve. Yeah, so because it's a multi curve, you have like, yeah. So yeah, that's why there is some classification. So that's just a one comment. Yeah. Thanks for the nice talk. Yeah. Thank you.
So is there any more questions? Any question or comment? Because yeah, we have 5 more minutes. So can you comment on some more examples
Of
some of taxonomy space, like maybe taxonomy space of torus, or maybe some example, like just through some examples.
right. So yeah, we have seen last
Yeah.
time that right here. Yeah. So any such surface, we had seen that it has some pair of band decomposition, right? If you remember,
Mhm.
and the number of curves on your surface, they are basically uh, 3g minus 3 in number.
Yeah, yeah,
But
yeah,
in case of torus, uh, it doesn't have such a band decomposition
yeah, yeah,
in it. So in fact, the Teichmuller space, if you see the definition of Teichmuller space, it is giving us like all hyperbolic structures.
okay,
And as the Euler characteristic of the torus is not negative, it doesn't. I mean, so there is no hyperbolic structure on your torus.
yeah, yeah, yeah.
So you need to define. You need to give a different definition of Teichmuller space,
Hmm.
if you may. So there can be some Euclidean structures on your surface,
Yeah,
okay, but not hyperbolic structures.
hyperbolic structure. Yeah, 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 yeah.
Yeah. And so if you have some pair of band decomposition, then you can of course talk about the hyperbolic. So you do this. So you cut along these pair of bands,
Yeah, yeah.
And as I discussed last day, that you can glue two hexagons from your right angled hexagons from your H2 and then come up with a hyperbolic, a finitely many hyperbolic pair of pans, and then you glue back so that the lengths are matching, right?
Yeah.
The boundary components length should match, and then
Yeah.
you have you have a parametrization of all such hyperbolic structures,
Mm.
namely differential-Nielsen coordinates.
Yeah,
Yeah,
yeah, yeah. It's good, good. So yeah, so I think for this hyperbolic structure, I think yeah, definitely uh, genus should be greater than equal to 2. Yeah,
yeah, right.
yeah. Okay, okay, yeah. So any other?
So I have a question. So that genus greater than equal to 2 is a sufficient condition. Is that necessary condition too?
No, of course not. I said the Euler characteristic should be negative.
Same
So
condition.
No, for what?
I mean, he
to
says that
have
torus
hyperbolic,
cannot have hyperbolic structure because its Euler characteristic is for 0.
Yes.
So it
Okay,
means
for that, for it being a hyperbolic.
okay, that's a necessary condition. For being hyperbolic, the Euler characteristic should be negative.
Hmm.
Okay,
Is sufficient also.
thank you.
so if you have the punctured torus, you remove one point from your torus that has hyperbolic structure.
Hmm. Hmm. Hmm.
Any other comments or any even small queries by any other participants?
Yeah,
Because
so
actually we
I
are
just want to mention that a standard reference for the theory of mapping class groups would be this primer on mapping class groups, written by Farb and Margalit. So you can, of course, you should look at the book if you want to. I mean, venture
so
more into.
maybe Soumya, you just share your slides also, and you write at the end this reference book so that we can share to the other
Sure, I'll.
participants. Yeah.
Yeah, sure.
You just collect all these slides, and at end you write maybe one or two books or whatever notes.
Yes,
Yeah,
yes.
so that I can share with some all the participants, because
Thank.
actually this is just the starting point of we are starting this lecture series, because our
Exactly.
preparation is basically for the next year CIMPA school, and
Right.
maybe in coming lectures, not even the couple of lectures by Jayadev, maybe in some more lectures we
Yeah.
will organize in future.
Professor Atreya
And
will be talking about the moduli space, right?
yeah,
So
yeah,
that's basically, so we have seen this mapping class group acting on the teichmuller space, right?
yeah, yeah,
And this moduli space is basically the quotient
yeah,
of this action. So if you consider the orbit space of this action, that's basically the moduli space. So yeah, we will see that in the first lecture of Professor Atreya.
yeah. In first lecture he will talk on what is moduli space, and in second he will talk on hyperbolic and flat structures. Yeah.
Yes.
Okay, so thank you so much for this nice lecture series of lectures.
Yeah.
And
Thanks for the opportunity.
I think yeah, sufficient background we have actually obtained. Most of the participants, especially from our university and other university students. So
Yeah.
okay, so I think at least we are ready for the Jaydev talk, and yeah, so slowly, because there are several students who are really hesitating to ask, but yeah, they are really beginners. So at least whenever they go back and will read the book, I think
Yes.
now at least they don't have any much problem at least understanding the basics.
Yeah.
So thank you very much, Soumya, and we'll see you on Monday.
Yeah. Bye.
Okay, okay, bye, bye. Yeah, I think someone has any question, or Anjali, do you have any question? No, 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 it's okay. Yeah. Okay, thank you. Okay, bye.